This video has been supported by ComMarker. Hey folks, we've had lots of fun with those ubiquitous overpowered blue diode lasers in the past. Their specified power ratings have become more and more crazy over the years, whereas their actual optical output power is probably approaching 10 watt continuous by now. That is impressive, not gonna lie, and useful to mark and cut many non-metallic materials. However, 10 watt is still a lot less power than the flame of a burning candle or a lighter produces, for example. Can you imagine attacking a piece of metal with a candle flame? Hell, even if you could focus the power of 2 or 3 candle flames into a small point, it would still be a pretty pointless exercise. Because metals are just so damn good at conducting the heat away from the point of attack. So we need a different strategy. Today we are looking at an early prototype of ComMarker's B4 desktop fiber laser engraver. It uses a Max Photonics MFPN 20 watt fiber laser source. That doesn't sound that much different, and it's still a lot less power than a candle flame on average. However, this is a pulsed laser that can take these average 20 watt and use them to pump a gain medium like a doped piece of glass fiber. The gain medium is like a reservoir for optical power, and it only takes a small nudge to cause a chain reaction and release it all at once. These short impulses of intense optical power can be in the multiple kilowatt range. Enough to instantly vaporize or explode away small specks of all the materials that blue diode lasers work on, and additionally most metals. That is why I've been hoping to get my hands on an awesome pulsed laser for a long time, and why I had to accept this YouTube video opportunity, even though I don't see a lot of value in analyzing early prototypes. But let's just roll with it. The ComMarker B4 comes in a nice and compact open desktop format. In terms of safety features, it is delivered with a $1 pair of green plastic goggles. And that's the end of that list. Minimal safety allows the manufacturer to deliver a capable machine such as this at a very competitive price. An individual home user who uses it correctly can benefit from this. However, in most professional environments, it is not allowed to use a dangerous laser with no technical safety features. It also came with a motorized 4th axis, which admittedly feels very nice. A focus aid for hand-holding the thing. Oh boy. And a foot switch, probably to help with semi-automatic mass production. The machine was delivered in 3 parts. The foundation, the Z-axis and the head. Those had to be assembled with 8 fasteners, and I had to flip a switch on the internal power supply, because it was set to USA voltage. And that is all the preparation that was required. Fume extraction is necessary if you want to work with polymers. Strongly recommended if you are only going to work with organic materials like wood or leather. And again, mandatory when working with metals because this process creates ultra-fine airborne particles. The filtration performance of my professional soldering fume extractor is sufficient, I think. But after having widened the pipe diameter of my BOFA a little bit, I feel like I'm not getting the required air velocities anymore. So either more suck or a thinner pipe would make this much more effective. The USB stick came with Windows drivers for a certain LMC V2U control board. That seems to be very common for these low-cost desktop fiber laser engravers. So there is motivation to get that supported on operating systems that end with X. And I've seen hints that it might already be possible. Just know that it's not included by default and it might cause trouble. To use the EasyCAD2 software that controls this machine, you must agree to an illegible contract. What could possibly go wrong? Oh well, I've sold my soul for much less valuable toys in the past, so there we go. Initially, the software complains about being unable to open a certain correct file. If I understand it correctly, that is a per-machine calibration for offset, skew, warp, and XY ratio. It should be delivered with every B4 engraver. Superficially, the software was usable for me right away, but it has a lot of depth to it. To align the focal plane, which is about 200 mm away from the head, with the workpiece you can use a hand crank or an electric gearbox motor with controls on the front of the unit. Both are coupled by a threaded rod, so when you're hand cranking, you're turning the output shaft of a gearbox motor. They don't like that generally. And yeah, it doesn't feel safe to hand crank a lot, as if you're about to strip some teeth. The surface is in focus when the 3 laser points align. That's a nice and intuitive method, although I don't quite understand why there are 3. Wouldn't an alignment of 2 laser points give us the same information? Maybe this is for the 1 in a million oddly shaped workpieces that just so happens to block one of the 3 points. Anyway, we are finally ready to send out some pew-pews. One of the 3 red points doubles as a pilot beam. It is delivered coaxially with the main working beam, so it can be deflected by the Galvo system and used as a visible preview for the area that is going to be engraved. As soon as we are happy with the location, we press mark and boom, instant success. This type of engraver is so fast because unlike our blue diode machines, it doesn't have to move around a big heavy gantry and an X-axis on top of that. It uses 2 lightweight mirrors to steer the beam, which allows the focal point to travel with speeds in excess of 1 meter per second. This kind of galvanometer steering comes with its own set of problems, and it doesn't help you if you want to remove material, i.e. cut through something. But it certainly allows you to cover areas with incredible speed. The correction file did its job well. My circle came out perfectly round, but approximately a % too small. No big surprise, as the scale of the projection depends a lot on perfect focus alignment. The biggest challenge when using a Galvo for laser scanning is that the focal length is a constant around the lens. You could imagine it as a sphere around that circuit board. But for engraving we want a plane to be in focus, such as that threaded base plate of the machine. Don't shine lasers at planes, kids, that's dangerous. Long story short, the special f-theta lens below the Galvo scanner makes the focal length a function of beam deflection, in such a way that a 110 by 110 mm plane is always in focus. This sets the usable area to pretty much 110 by 110, but the machine is larger than that, and larger, more expensive lenses are available. Another important component in the head assembly, usually a part of the fiber laser source, is the output isolator, whose primary purpose is to prevent laser radiation from being reflected back into the source. But it usually also expands the beam a bit so that we don't engrave the Galvo mirrors, and stay clear of the damage threshold of the lenses. The included safety goggles really are remarkable. I don't expect a low-cost machine to come with free high-quality PPE, but out of all the cheap pairs I got over the years, this one absolutely takes the crown. It has a matte surface finish, as if it has been exposed to some corrosive vapor. I mean, if the plastic is a reasonable attenuator for the wavelength in question, a rough surface finish won't change that. But shipping something so unpleasant with your machine will encourage users not to use it, and subsequently endanger their health. Here's my finest pair which I'm going to use for this. A bit of an overkill for a 20-watt engraver. But then again, for eye protection, is there really such a thing as an overkill? Its plastic sides are metal reinforced so that even a few joule headshots are unlikely to ever reach your retinas. Here's how they are labeled in Germany. D stands for dour or continuous wave. I stands for small impulses and R stands for Riesen impulses, so large ones. And M stands for mode locking, i.e. pico and femtosecond lasers. What do you think? Should we look at a femtosecond laser someday, since I already have the goggles? The central column is the usable bandwidth, and the L numbers are the attenuation for every row. The higher the better. For a 20-watt 1064 nanometer fiber laser engraver, I'm feeling reasonably well protected in the 7 neighborhood. Let's try and engrave this pair to see if it is a good attenuator in the 1064 nanometer wavelength. Yeah, it did something. Yeah, pretty good. We don't know for sure how much went through, but this provides some protection at least. The line width is very impressive, I must admit. I've not yet seen a diode laser deliver anything close to this. The manufacturer has just replied to my opinion about their safety goggles. For what it's worth, they are going to offer a better looking pair with the final version of this machine. Let's test how far we can go with this impressive minimal spot size. I've precariously pointed my microscope at the center of a planned test engraving, where I want to use smaller and smaller text sizes until we can't read it anymore. And here we are live and up close at the event. Wow, that is impressive, and it can be even better. If we don't fill the contours, use a lower power, and go only 300 mm per second, we are getting a perfectly clean, crisp 0.4 mm height text. 0.3 mm should also still be legible, but 0.2 doesn't work anymore, with no settings that I have found. I wanted to try and fine-tune the minimal spot size even further, and realign the 3 red dots on that height. But it turned out that the factory setting was already optimal, and over roughly 2 turns of the Z-axis lead screw there are practically no changes in the spot size diameter. So this is as good as it gets, and that is very good indeed. But removing aluminium anodizing die has been an easy exercise for our continuous wave lasers in the past. So let's finally get to the point and remove some metal. This dog tag I think is chrome-plated aluminium. It's going to get Dexter's name on one side and his return address on the other, should he ever get lost in the neighborhood. I imagine you could start a small but profitable business making customized gimmicks like this for people, or custom engraving their jewelry and phones. But careful, the Fresnel equations of absorption and reflection of various wavelengths in various materials still apply. So not every victim will be as beautifully receptive to 1064 nanometer bombardment as this. Here I've hot glued a macro lens to my smartphone camera to be able to capture some slow-mo footage of the working beam in action. The pink-looking light is as always the smartphone camera's representation of infrared. The high brightness at the point of impact is probably overheating and oxidizing of the coating and partially of the metal below. The sparkler fireworksy effect makes me believe that we are not only evaporating metal, but also literally exploding away some solid particles through rapid thermal expansion. Beautiful. Another advantage of this pulsed operation is that the material that we choose to pew out of existence really is mostly gone before it has time to pass on some of its heat to its surroundings. That allows us to work on sensitive parts without overheating them. For example, precision resistors receive careful annealing after manufacturing. If it gets massively overheated again after that, its properties are permanently degraded. Trimming of a current shunt in circuit would probably only take it to 40 Celsius, which is great. A lot less detrimental than 280 degrees C reflowing. Although the most immediate neighborhood of the cut might suffer a bit. That's why resistors made for laser trimming use these stepladder patterns. When a rung is cut, almost no current is going to go in there anymore, and experience the degradedness of the area. Let's try a cheap, light, soft wood. Nope, it absolutely wouldn't, not even with full power at a slow speed. This is normal and well known for infrared fiber lasers, they just don't do so well with lightly colored things. It can't even a piece of tissue paper. Neither my pale cellar-dweller skin. That's because I just don't have the pigmentation there to absorb the wavelength effectively. It is able to bleach my hairs though, and I think it could attack some tattoo dyes, although with the extremely small spot size it might be an extra long and painful procedure to do a full tattoo removal with this. I'm afraid it might also hurt stronger pigmented people, so fiber lasers are confirmed racists now. Darker, higher quality woods work a little bit better, or just painted pieces. How do you like my ripple clamp? Get it? It's a ferrite core on a... No? Okay, next. I am beginning to feel somewhat comfortable about the EasyCAD 2 software. It is very powerful, but as I said, very deep. It seems to be the most common software to be delivered with fiber laser engravers, so there are lots of resources on the internet. I'm going to set up 3 text objects, and for the central one I'm going to enable the variable text tool. Here you can engrave a string from all sorts of data sources, like an automatically advancing serial number, a date code, a timestamp, something from a serial port or a keyboard input, or even from an SQL database. And I've connected the foot switch to the machine, now I'm getting 1 engraving per press. I think I found an advantage of 3 over 2 dots. This way you can do focus adjustments while at the same time a preview is being shown. This kind of semi-automatic setup can be a huge time saver in mass production. And who knows, maybe we can do a small 80 RMU 10V standard production run, if there is any interest. But to be honest, DIYing and fine-tuning these yourself is most of the fun. Originally I intended this white solder mask field for handwriting. For fiber laser engraving it's not optimal. I'm giving it full power and 3 passes to make it look good. But yeah, this is a fantastic option to have. The threaded grid plate of the ComMarker B4 allows you to mount all sorts of fixtures, for various other workpieces too, but I have a small suggestion for an improvement. I think it would be best to make these blind holes, because the engraving process creates a fine dust which can sometimes be conductive and therefore wouldn't be welcome in the sensitive circuitry below. So since this laser removes some material, it stands to reason that it could also be used for depth milling. This is about 1 millimeter of aluminium and I'm going to try and cut a hole in it. Yeah, it will work eventually. Other YouTubers have demonstrated this. Steels cut significantly faster because they are not as thermally conductive as aluminium. And of course a 50 or 100 watt laser source would accelerate this massively. But I gave up after getting a headache from half an hour of wearing my goggles. Maybe 1 or 2 hours would do it, but certainly the B4 is not suitable for this. It doesn't claim to be. I just wanted to give it a try. Thin stainless steel sheet like solder paste stencils or razor blades are of course only a matter of seconds. Stainless and titanium are very interesting victims to fiber lasers, because by dispensing just the right amount of energy into a surface, you can make it grow a thin oxide layer, which can give a workpiece interesting permanent color effects entirely without additional chemical dyes. MOPA fiber lasers like that SPI unit we've taken apart once are especially nicely suited for this, because they give you maximum control over the impulse timing. But it works with Q-switched models too if you do it carefully. I'm not entirely sure yet how the Max Photonics laser source in the ComMarker B4 works. I have a Chinese manual for it and in there both the MOPA and the Q-switch keywords are mentioned. So I'm afraid we really have to take it apart a bit further. The rotary axis that was included in this bundle is very cute. It's basically a spring-tensioned 3-jaw lathe chuck mounted on a stepper motor. It feels like it's made from carbon steel, so when not in use for a long time I would oil it, so that it doesn't rust. There are a few different kinds of pegs that can be screwed into the jaws, for gripping various shapes. The jaws can also be reconfigured between normally open and normally closed, simply by reversing the spring. Just like the machine itself, the stepper motor driver for this axis has a prototypey construction quality, because I suppose it is one. I had to reseat the enable wire in here to get it to work. Other than that, the manual told me fundamentally how to operate this additional axis. Further details are available in many YouTube videos. In keeping with its tradition, EasyCAD 2 doesn't make it exactly easy, but it accommodates many accuracy and speed levels, as well as rotation around the X or Y axis, or wrapping the flat image around angular stock material. In short, it needs to be complicated to be universal. I prefer that over some oversimplified but ultimately crippled software. Okay, we've got to hurry up a bit. The manufacturer wants this released today. This is an alumina ceramic substrate, an electrical isolator and a thermal conductor. It's interesting for microwave circuit boards and thermally coupled assemblies in DC metrology. One of my Discord server members has kindly chemically activated two and copper plated them for me, for testing as a thermally coupled resistor network. I have ordered some fresh materials for the laser-induced selective copper plating recipe by Breaking Taps et al. Last week, but nothing has arrived yet. So unfortunately I can't show selective copper plating today. But what we can do is score these ceramic substrates, which is nice enough in my opinion. I find it amusing that we can protect the sensitive anodized aluminium baseplate from accidental laser marking with an invincible piece of tissue paper. I know what you all crave. Will it circuit board? This is a photosensitive pre-coated Bungard FR4 board. It seems to be some kind of German specialty because whenever I'm using these I get tons of questions. Basically, when you are preparing for chemical etching, you can simply spray some copper-clad material with a spray paint rattle can, and then remove the coating with a laser wherever you want the copper gone. With its very small spot size, the ComMarker B4 is excellent at this. Much better than the blue diode lasers we had in the past. This is the bottom layer of the Orange Crab open source FPGA board, by the way. Plotted in KiCad as a DXF, imported into EasyCAD 2, and contours filled with diagonal hatching. This part of the video is playing in real time, so it's wonderfully fast too. The next step would be a lengthy bath in ferric chloride solution as an etchant, for example. Or some recipe with peroxide could be faster, but you might end up on a government watch list. At any rate, I imagine chemical etching after this would give us beautifully clean results, in spite of the small feature sizes on this board. But since our pulsed laser is also able to ablate metal directly, why don't we take it one step further? There is a company not far from where I live that makes laser machines specifically for rapid PCB prototyping. I imagine those LPKF proto-lasers will cost 50 times as much as this thing will be. So this will certainly not give you the greatest performance ever. But I have to say, after only a couple of minutes at 90% power, this is undeniably a directly laser-etched PCB. Timing is crucial. You can't let it dig too deeply into the substrate below the copper, or else small features will overheat and delaminate. I think with direct engraving, the smallest possible feature size isn't quite as good as with chemical etching. But if you're in a hurry, this will most definitely give you circuit boards. One more concern would be that overheated substrate will carbonize, and therefore have a lower resistance and allow for more leakage currents. But still, this would have been a dream for me a few years ago. Nowadays I don't think I'm going to use it that much, because Chinese circuit board manufacturers are just so cheap and fast and good. Let's hope it stays that way. And my final exhibit for this video, we can of course obfuscate plastic molded IC packages to slow down reverse engineering attempts. Love it when manufacturers do this to disguise their STM32s, but then leave the memory unlocked. Ultimately, if an attacker has unlimited access to a device and some resources, this is a pretty weak protection from reverse engineering. Because you can just give it another minute or two under the laser to remove most of the plastic. If you're interested in taking a look at the silicon die, where there's usually a manufacturer logo and a part number, it's very important to stop lasing early, because the semiconductor features are at the very top surface of the die. A single round of 1064 nanometer bombardment will make it illegible. The last micron of plastic should be removed chemically, with warm nitric acid for example. In this case I didn't pay much attention and I went too far, unfortunately. Calling the internal construction prototypey is a compliment for this cabling chaos. The ground wire for the laser source, for example, has been placed underneath the mains power supply, which was then screwed down, squishing the ground wire in place. It takes an experienced technician to understand that that is, honestly, effective. Better than nothing. And it takes quite a bit of attitude to send something like this to a YouTuber who is known for taking everything apart. Let's go all the way and take a peek into the fiber laser source. Ugh, no thanks. Let's get the hell out of here. I'm just kidding, it must have survived my tests so far, so it can't be that bad. But it sure looks bad. Oh, never mind, that's cute. I've never seen blue fluorescence from a fiber before. No idea what that is doped with. All I can say is that the forward-facing elevated section of fiber is the doped gain medium, because it has been arranged with a modicum of care and siliconed to that plate for a bit of heat sinking. I think this is a power sensor, because its black cable goes to ground and its red cable goes to the inverting input of an op-amp. I don't like this bird's nest with its uneven infrared fluorescing peaks. Since our SPI adventure I've adopted a few more broken fiber lasers from eBay, and all had some kind of exploded fiber in a tight bend or in a junction. Still, all looked neater than this Max Photonics miniature model. Looks can be deceiving, but I'll be watching this one closely, and if it dies soon, I'll report about it. I came here to find out if it's a master oscillator power amplifier or a Q switcher. The manual for some reason mentions both technologies. It's tandem pumped by 3 18-watt fiber-coupled diodes. And over here we've got a... oh no, I hate this. I hope that's a strategic, intentional bend radius violation, as an attenuator or filter, and not just a way to tug away some extra fiber. The coax cable that we've seen leave the mainboard on the other side of this module could either go to a seed source, a fiber laser that's good at producing impulses, which would mean MOPA, or to an acousto-optic modulator, a Q switch, a crystal that just isn't very transparent unless tickled by its favorite frequency. It is obviously the latter, because the recipient of that coax cable starts with Q. And it has a fiber in and output. The seed source would only have one output. So this is a Q-switched something doped fiber laser, and my curiosity is satisfied. In conclusion, this ComMarker B4 prototype is an amazingly fun toy, for a huge variety of nerdy activities. This video could be twice as long and I still wouldn't run out of ideas. It does everything that I would expect from a 20-watt desktop fiber laser engraver. The competition in this field is huge, however, and the prices have been dropping like crazy in the last few years. I'm not seeing any crazy innovative features that no other manufacturer has ever delivered. The rotary axis is cute. The minimal spot size and the accuracy of the optical system are as good as they get in the category of affordable fiber laser engravers. At the time I'm speaking these lines, I have not yet seen how the manufacturer is going to advertise this machine and how much they want for it. I think it's going to be a crowdfunding campaign, and for that I have to ask you to do your own research regarding trust in the manufacturer, the platform and their terms of service. The pre-production prototype above us is mostly nice, that much I know. If it wants to be taken seriously as a professional, productive, lucrative tool, I think it has to do more to comply with Class 4 laser safety regulations. An interlock input connector or two would be good, for example, if a user wants to build their own enclosure. And for this remote handheld mode, I need kind of an output active indicator, so that I know 100% when I can move again. And a stop button please, because if I change my mind in the middle of an operation, I might not be in a position where I can reach the base. And that's all. Thank you for watching. Check out the link below if you want one.